Right. Hello, everyone. Happy Friday. Welcome to CS109. Now, I am not the usual person. Chris is here. He is well. It is only customary for the head TA to give the lecture on algorithmic analysis. So, in continuing with that tradition, here I am. And we have a good amount of content today. So the coverage today will be expectation, law of total expectation. We have 5 problems prepared today. Of those 5, one of them is extremely difficult. So I'll give a bit of a heads up and a warning before that, throw around some candy, get some glucose going for that problem. And then afterwards, it's more or less straightforward. So yeah, let's have a good time. Happy Friday. Hope the last week was good. Cool. Oh, by the way, so the bribery today is we got Kit Kats, and we got some chocolate truffles, and I'll throw these in uniform random distribution weighted by how many there are. Okay. All right, and with that, let's get started. A little bit about what happened last time. There's a null hypothesis. So how can we use bootstrapping to deal with null hypothesis? So this will be a little bit of a review, but the idea is we have this thing called a p-value. And the one kind of crystal idea that we really want to get across is the p-value is the probability that your hypothesis is from noise. And that's why we can do bootstrapping with like replacement as samples, just to say, hey, if I got these 2 different samples and I just take like subsamples with replacement, what is the probability that I'll actually see the hypothesis that we're trying to claim just out of random noise? That's it. P stands for, what did I just click? I didn't click anything. Okay. P stands for what's the probability that your hypothesis is just from noise? That's it. Okay? All right, so on to the main topic for today, algorithmic analysis. And one of the problems of the 5 that I said we'll cover today is pertinent to Netflix streaming. So in particular, the caching system that Netflix had up until I believe like a year or 2 ago when they switched over to AWS. But those are things in the news, but we'll see how they actually like stream some of their videos. Okay, so, but first we should do a little bit of a review, especially about expected values. So fundamental definition of expected value, how do you calculate the expected value of a random variable? In here, we're assuming that it is discrete. So we take a sum over, x is the value that each random variable can take on. Probability that x takes on that value is just like p of x equals x. Okay. This should all be review. This was like from material from before the midterm. Okay. So a little bit more general than just the expectation is linearity of expectation. So when you have the sum of some random variables, you can just carry the expectation into each one of the terms. So why is there 2 clickers on this? Interesting. So the expectation that of a sum of random variables is equal to the sum of the expectation. Now we'll be seeing this a lot in class today. Like I think there's at least like 5 other slides that have this particular that have like switching this little e with this big capital sigma that kind of looks like an e. So it'd be like the big E, little e switch. There's a few slides of this. Okay. So here's one kind of limitation about what we can do with expectation. The issue with expectation is it tries to capture all of the characters of a probability distribution using a single value. So this is good and bad. Good as in if the underlying distribution is just way too hard to capture, we can at least give some kind of a reasoning about it. The bad is it's a single number. Like I can tell you what the expectation here is of this big curve, but sometimes what we really care about is like, okay, what is going on in this like 7,000 range? It's like, that's your tail. Like you should really be optimizing for your tail in certain situations too. So we'll talk a little bit about like how that kind of plays into like software selling or so, but this is the primary limitation of expectation. Okay? All right, so a couple other things, law of unconscious statistician, just expectation of a function on some random variable x is equal to the sum of the function on the values that x can take on, multiplied by their probabilities. And then one particular example that we see, probably like I think on the midterm too, was when we're calculating the variance, the terms are expectation of x squared, like x the random variable squared, minus the expectation of x the random variable all squared. And for that first term, the way you calculate it is you just take the output of any of the event values any of the values that big X can take on, little x's, square it, and then multiply it by the probability. Okay, so there's a lot of unconscious statistician. The idea is like, so it's quite simple, and an unconscious statistician could do it, but it's debatable whether or not we can like recognize it immediately in the wild. Okay, so that's all for review, and here are some kind of like practice problems and revisiting a few of the random variables that we've seen so far. So first of all, let's start with bool. So let's say we have some events E1 through En, and they're indicator random variables. Okay, so what does an indicator mean? Indicator means Bernoulli. Okay, and if each of the Bernoulli random variables occur, if they occur, your Bernoulli is going to take on value 1. If it doesn't occur, then it's going to be 0. Okay. So we have said in the past that the expectation of whatever the Bernoulli random variable is equal to just the probability of the event. Yes.
How do we know that indicator means Bernoulli?
Oh, it's defined. So it's defined. Like the indicator is really defined as to be the function where if the random variable occurs, it's 1. If the random variable does not occur, it's 0. Okay. Yeah, this pops up in 2 examples, so we should clarify that now. Okay. So why is this the case? We we just expand using the expectation. The 2 values that the Bernoulli random variable can take on is 0 or 1. Multiply them by the probabilities and take a sum. Okay, that's it. So here's a term that should be used a little bit earlier, but Bernoulli, also known as the indicator random variable, were studied by the guy named George Boole, and Boole actually died of being too cool. This is exactly how he died of pneumonia after walking around in the rain in Queen's University or something in England. Okay, so in other words, don't run out in the rain and be cold. I think I've seen 2 rainstorms here in the past quarter or something. So take care of yourselves. Don't be running around in the water, right? It's a big cold for that. Don't get pneumonia. Okay. So a little bit harder, binomial. So we've kind of alluded to, or at least I've alluded to in my section, that a binomial is just a sum of Bernoulli random variables. So one thing that we could take is, take each Bernoulli random variable, take the probability, say there's n independent trials of them, define the indicator variable over them. By the way, indicator variable, Bernoulli random variable, they're kind of really similar here. Say each indicator variable is from a Bernoulli, take the sum over them. Okay, so this is the sum, and y here is actually a binomial. So y can be defined as both the binomial here, or it can be defined as the sum of Bernoulli random variables. Okay, with the same p for each one of the Bernoullis, IID, etc. Okay, how do we take the expectation of this? We take the expectation on the outside of the sum, switch the big E and the little e, and we get that the expectation is just the expectation of the sum is the sum of the expectations, which is just n of the random variables times the probability for each. Okay, make sense? All right, cool. Expectation of a negative binomial. So in class, we've seen that the negative binomial is the number of trials until you see R successes. Okay, until you see R successes can also be modeled so R successes, each one of them is the number of trials to get success after the I minus first success. Those can be modeled as geometrics, and then the negative binomial is actually just a sum of the geometric random variables. Okay, so as a pattern with binomial random variables, we will be taking the expectation over these and just switch around the sum and the expectation, and we get that the expectation of a negative binomial is exactly as we will expect, R trials divided by total probability of P for each. Okay. Make sense? Real good? We're just using the same trick over and over again. Just swap your expectation with your sum. This is a key idea. We use this all the time in 109. It's pretty important. Okay? So with that, let's move on into the first of the 5 problems that we have today, computer cluster utilization. So consider if you have a computer cluster with k servers. That means you have like k little desktop towers all running some program. Or you have one single desktop tower running k different programs. Requests are independently go into each server. So call one of the servers server I with some probability pi. Okay? Let AI be the event that is server I has no requests. Okay? So actually, maybe it would be helpful to do board work for this one. So if I have these like 5 different servers, right? Or 4 of them for now. And there's like S1, S2, S3, S4, okay? And then the number of requests that I have can be like R1, R5, R10, okay? Because the other ones have gone processed or so. S1 here does not have a single request it's processing, so it's sitting idle. So in this case, the A indicator variables would just be A1 equals 1, because it's true that S1 is blank. Then there's A2. Oh, by the way, is this too small for people to see? Okay, cool. A2 is 0, ... All of these are, A4 is 0 as well, because they all have a request for servicing. So each of these A's just monitors if a server is idle or not. Okay? So X is going to be the sum of A1 through AK. So the total number of servers that are idle. And the thing that we want to kind of monetize, or the thing that we're like really interested in, is what are the number of servers that are actually doing useful work at this like point in time with this many requests. So the question here is, how do we go on ahead and solve for the expected number of servers Y that are not vacant, given like some certain number of requests? Okay. So let's see. Okay. So maybe like take a minute or two, discuss a little bit, and see how we can kind of solve for expected value of Y here. Yeah, maybe like turn to your neighbor, find someone nearby to talk to, or just like shout an answer. Yeah.
So it's not the expectation of a single variable, but a bunch of random variables. So you have a bunch of variables, you're going to add this back to the expectation. And we're going to do expectation for each one. So are we going to...
Okay, maybe let's come back and solve this as a group a little bit. So Y is defined as, so I went on and cheated a little bit and clicked on the clicker for a little bit of a start. So Y is defined as just K, the total number of servers that we have, minus those that are idle. So by linearity of expectation, we can just say, okay, expectation of Y is equal to the expectation of K. Expectation of a constant is a constant. and then propagate it to the expectation of x. So here, okay, now we just need to solve for the expectation of x. Okay. For the expectation of x, we know that, okay, so what do you know about x? X is the number of events of a1 through ak and their indicators. Okay. So that's just going to be the expectation of the sum over all the indicators. Okay. Does that make sense? Anybody have any questions? Yes.
Where's the formula for y coming from?
Oh, here. Request, yeah, it's equal to k. Yeah, this is
So it's just given.
yeah, it's given.
Like a logical reason why that's the.
Yeah, totally. If x is the number of servers with 0 requests, the number of servers with more than zero requests are all the other servers, right? So there's k total servers.
Okay.
X of them are idle, and we're looking for the ones that are not idle. So that's just k minus x.
Okay.
Yep. Okay. Oh, I should be giving out bribes. Here, Kit Kat.
Oh my god.
Yeah.
Thank you.
Okay. Any other questions? I got plenty of Kit Kats here.
Can you just repeat again what BI is?
BI. So BI is the Bernoulli indicator for the AI. So actually, AI here can already be modeled as a Bernoulli just by itself. But we explicitly say, hey, we know that this event AI, that like a server I does not have like a request, is either true or false. But to kind of cast that true or false to a 1 or a 0, we need to say that it's an indicator. Like this is useful for if you make an assumption over like the probability of like your K servers being idle or not. And in this case, it's kind of like, okay, like semantically, we could just say AI equals, like BI equals AI, and it will be the same difference. Okay? Yes?
Can we always just encapsulate all of the individual terms in linear equation as expectations? And are there any specific cases where we can't do this? Because we had y is equal to k minus x.
Yeah.
And then we just apply the expectation to both sides.
Yeah.
We have a value that's always going to be valid.
Oh, yes. It's always valid. Even like kx, it could like x could be dependent on k could be dependent on x. If you have a subtraction and you're interested in the expectation, just propagate that expectation to each term. Expectation is linear, which is like super cool. Okay? Oh. Sorry. Okay. Anyways. Okay. So okay, we do the usual thing. We swap in the expectation into the sum. Then we calculate, okay, what's the expectation of each one of the indicator random variables? It's going to be the probability of each AI. That's just equal to the probability of each request going into a server times the number of servers there are, times the number of requests there are, n, or to the power of n. And then there's going to be k of those. So that's it. You like there are n requests. The probability that one of them will go into each server is 1 minus pi. And then there are k different servers, so you just sum across them. Okay? Yes.
When you go from E of BI to PAI, is that because the expectation of each?
Exactly. Yeah. So to repeat the question, going from E of BI to P of AI here, this is because the expectation of Bernoulli is just a PI. It's just a probability. Okay? All right. So why is this important? Because Amazon actually uses this in AWS. They say the number of servers that are occupied at all times and the number of servers that are idle at all times has a direct impact on their efficiency and how much money they're spending on their like AWS like computing warehouses. And they can actually monetize this. And okay, yeah, there's a drone that they made a while ago. But the important thing is AWS Web Services is actually 52% of all of their like profit. Like that's more than their like whole North American commerce operations. So like everything that we use on like the Amazon website, that's like they make less money from that than they do from just like AWS like services. So like the idea is like they rent out these computers. They're like elastically sized for consumers to kind of like rent out the computers, and they can make money in the fact that your consumers are not going to always be using your computers. So like there, like you could shuffle around the consumers on each computer and make money off a like kind of renting out compute. Okay. All right, so yeah, that was pretty cool. This is a pretty big game changer. A lot of people started doing like cloud computing for this, like Azure, GCP, or AWS. Yeah. Okay. So remember how I said I'd give a warning before the problem? That's going to be the hardest in this whole lecture. So, a little bit of background about this particular problem. It's a name problem. So we gave this problem out, I think, a few years ago in like a final exam, and I cannot understand. Well, it was very difficult. It's particularly famous, and I've actually like when I first got the slides, I like wrote like quite a few more slides just to kind of give it like more motivation about like why this problem is important. So if the last like example kind of like we went a bit too fast on, it's because like I really kind of wanted to like save some time for like this particular example. Okay. So before we start with this one, anybody want a Kit Kat? Oh my God. Okay, this is gonna. All right.
Can I deliver the Kit Kat?
Yeah, sure. Yeah. Oh, okay. Or you can just. Okay. Here. Here. Josh. One here. Okay. Sorry. Okay. Let's go to the back. Okay. So there's 2 this way. There's, looks like, let's see, 1, 2, 3 that way. Sorry, okay. This is probably not gonna work, but okay, we're gonna, whoo. Whoo. Okay. Whoo. Oh. Sorry, keep it. Okay. There was a spread, okay. Bro, don't allow me. That's a no, that's a no. Huh? Oh, yeah. Oh, I'll put it, it's here. Okay. That's lecture code. Okay, all right. So that's, okay. Let's hit the hard question then. Get some glucose. It's a Friday. Let's not check out just yet for the weekend. All right, so here's another key for this problem, okay? When stuck, just brainstorm about random variables. It will be very good to like, kind of like, okay, just like start thinking of very creative random variables because like when I saw this problem, I was thinking, geez, I could not do this on the final. But, okay, so here's the premise. You got a hash table with n buckets, okay? You have a set of strings. Each string is equally likely to get hashed into any bucket. So just like you have a very good hash function that just equally distributes these strings, okay? Let x be the number of strings to hash until each bucket has more than or equal to 1 string, okay? What is the expected value of the number of times you're going to have to hash a string? That's it. This singular question has a name. It's typically called the coupon collector problem. And I've seen it in about like 2 or 3 classes. First time I saw it was in 109. Second 2 times were in like other CS theory classes. Pretty popular. It's got a really nice solution, but it takes quite a bit of motivation if you're seeing it for the first time. Okay? So, to kind of demonstrate, here's a hash function. Here's 5 buckets, all right? We're going to start hashing some strings and get a little bit of like motivation about how we can solve this. So we have a string, okay? Here's a string. Our CS109 students are the best. We hash it, and it gives us a little sun in the first bucket. By the way, this is going to be like all the strings are going to be like subliminal messaging for please feel good on a Friday, okay? So this is round 1, okay? So x here has like, well, okay, it's not x, but like the number of rounds here that has happened is 1 because we've only hashed 1 string. Okay? Here's round number 2. We hash this other string into the third or fourth bucket over here. Indexed by 1, indexed by 0. Then we hash another string, and this is round 3. So now we have a collision, and we put 2 suns in the first box. Okay. Then on the fourth one, we hash another string, and it puts a smiley face. And yes, please eat fruits. There's sickness going around. Hopefully this will help. This puts a smiley face into one of the other buckets. The only two buckets that we have to cover now is the bottom bucket here and the middle bucket here. Once we cover those two, we're done. Okay. So we hash another string, and we finally get a little symbol in the bottom bucket. But we hash another, like, okay, so now we'll be done if we hash a string into like the middle bucket, right? Yeah, but sadly, I put a heart in like a little weird place because we need a space for another heart. So we don't actually get what we want. We have another collision. Okay, and then finally on the 7th round, we're actually done. Okay, so the value that x took on here is 7 because it took 7 rounds for this whole table to be filled. Okay, did I go too fast on that? People good? Do we understand the premise here? Thoughts? All right, cool. So the question is, what is the expected number of rounds? All right. Okay. Maybe turn to your neighbor, talk about it, come up with some good ideas for random variables that we can use here to try to solve the expected number of rounds. A few good considerations are like maybe there's something geometric in there, maybe there's something like binomial looking in there. All little suggestions, but yeah, this is not like one could probably think of it like a span, like with fresh eyes can think of it like a span of like a few minutes, but like it's the one that we have is pretty hardish. Okay, go for it. Do you guys want a little bit more time, or think we could take a stab at it? Oh, all right. So okay, so who's got a good suggestion? Tell you what, for these ones, I'll give out chocolate truffles. Okay, yes.
I don't know if it's a good suggestion, but I was thinking like.
Can you speak up a little bit?
I don't know if it's a good suggestion, but like if we have n buckets, then you can like think of like each bucket as being a success. I was thinking like in geometric, where like each bucket would be like a success for that one, and then it would be like a sum over a lot of them. So it would be like something with like a negative binomial, something like that. I don't know.
Great suggestion. So I like that. So there's, I heard like sum of geometric, something about binomial. They're very good. The only issue with the binomial is it assumes that they're independent of each other.
Yeah, I was thinking like a negative binomial, because a negative binomial is a sum of geometrics.
Negative binomial or a sum of geometrics. Yeah, but then you need to like. I had the same thought last night, and I was trying to see if I could explore it a little bit more, but I think the way that the approach that we actually have is like pretty close to a negative binomial, but it's at stages. It's kind of quite close. Here, can you pass this back? Can you pass this back?
Oh yes.
Yeah. To the gentleman over there in teal, gray, blue. Huh? Okay. Thank you. Okay.
What if we did a summation of different geometric random variables, where the first geometric, the probability of a success being picking a new bucket is exactly 1, so we're for sure going to get a success. Then each subsequent round, the probability lowers, therefore the expectation of the geometric 1 over p is going to get greater, and we just add all those up.
Okay, yeah, I'm pretty sure that's 80% of the solution. We can go with that. So what I suggested was using a geometric at each round, and say that quantify success as a new bucket at every single round. So what this means is let xi be the number of trials to get a success after the ith success, okay? So what does success here mean? Success is hashing strings to previously empty buckets. Okay, and after I buckets have like greater than 1 strings, like we can calculate the probability of a success as being like n minus I divided by n. Let me clarify what that means. So we have a string, we have some partially filled area here. There's like here I equals 3. There's 5 buckets, and we have this region over here of like 3 kind of like consecutive buckets of just like emptiness. I put them consecutive. They don't have to be consecutive, but they're just there. It was easy to draw. So here we see that like the success here will be like hitting any one of these 3 buckets. Okay, and the geometric variable that we're going to be looking for here is we already have like I strings that are like there's already two successes here. There's 2 of them, right? There's like 2 buckets that have strings already. They've satisfied our criteria, and the probability that we're going to hit any of these is n minus like I divided by n, which is going to just be like 3/5. Okay, so that's the probability that we're going to be successful at every round from whatever the ith round is that we have here. Did I say I as a sum? Okay, I just realized. Okay, anyways. So the random variable we're going to choose is a geometric, and it's going to say, okay, after the 3rd round, what is the expected amount of time until I throw like throw a string into one of these bottom 3 buckets? Okay, does that make sense? This is like the critical piece. Like this probably like this single little thing here, like this little like. Thinking of this really creative random variable probably took like many hours of trying, or like I don't know, takes nothing. Okay, any questions? Like I don't want to lose people at this one. Yes.
Why is I greater than 2? Since we already have.
Yeah. Okay. So I have here's a typo.
Oh,
round here, so I wrote the round here is like I should be 2 here. The rounds are like I counted rounds and number of buckets as a, even though they're not. So this is like these sides are like written at like these sides this is supposed to be a 2. I'll correct them before we post this, but yes.
So to clarify what's happening here is that we're studying a bunch of geometric functions, and we're summing the probabilities together because every single time, the chance that you're going to fill an empty bucket is going to be lower.
Yeah.
And so we'd only sum 5 probabilities this time.
For this one,
5 geometrics.
5 geometrics, not just 5, right? Because you could like, actually yes, you'll sum 5 geometrics.
With the chance, you can have multiple rounds, but like.
Is it 5 geometrics? No, it's not 5 geometrics.
On the 5th
It's like-
round, the chance of success is 1/5, so the expected is 1/1/5, or 5 expected trials.
Sorry, could you repeat that?
It's like, wouldn't you sum 5 different geometrics? For example, on the first round, the expected number of trials is 1, because the probability of success is 1. 1/1 is 1. The 5th trial, the probability of success is 1/5.
Yes. You sum n. So you sum for the number of buckets that you have.
I think I have.
Yeah. You do some numbers. The thing that was unbounded is the geometric itself is unbounded because it could take you like an infinite amount of time to actually hit each one of the buckets. Yes.
How do we get P? Like, so like n minus I, where's that? Or is that?
Sorry, could you repeat?
Yeah. Where does P come from?
Where does P come from?
Yeah. Like what is n minus I?
Oh, n minus I is just a number of buckets that don't have a string in it already. And then divided by n is like the probability that you're going to hit any of those probabilities for this one particular, for like the next round.
Oh.
Yeah.
Okay.
Okay, all right. Let's move on. So okay, here's the full here's like the full like geometric PMF of it. Your xi's are going to be distributed with geometric n minus I divided by n. Okay, so this is the main important part. The part that comes after is just a bunch of mathy math, and like there's something complicated about those, but don't worry too much about it. So the part that comes after is not that part, but you take the expectation, it's n divided by n minus 1 as defined by the geometric random variable. You take the sum, exactly as we said, over here there'll be 5 of them, so x0 all the way to 5 minus 1, 4. Okay? Because you have 5 different buckets, or here n different buckets. You sum over the probability for all of them. And then there's this thing, which is okay, if we really wanted to compute it, each one of those xn's has probability like n over n. Like the first bucket you're gonna fire off, probability 1 that you're gonna hit an empty bucket because that's the first thing you're gonna hash. Then after that, it's like okay, now I gotta hash the other n minus 1, and then after the second round, then you have to hash like I don't know the next like n minus 2 buckets, right? So this particular sum has a name of a harmonic sum, and in math, and that particular harmonic sum is some constant times log of n. That's it. There's no like I actually tried to figure out what that O was. It was actually like bounded between like two little log things. It was easier just to say okay, like it's like big O of like n log n. Oh, by the way, the outer n is from like the n in the numerator, or n in the numerator. I forgot I had this clicker. Okay. And yeah, that's fine. And yeah, this part right here will be your final answer. If you get this part right here, your grader will be very happy to see that. But that's about it. Okay. All right. So that's the end of the hard part. The rest of this lecture is going to be about this one cool like cache farming thing I saw. Some little things to help you out in like 161. And this one little thing about, well, not one little thing, like a pretty important thing about differential privacy. Okay, so what did we just see? We saw expectation, we saw conditioning, and as all good things, whenever there's a slide with a peanut butter and jelly sandwich, it means we're putting the two things together and getting conditional expectation. Okay, so for conditional expectation, have one. X and Y are jointly discrete random variables. Okay, recall that a conditional PMF of X given some y is equal to little y is just this like expansion here. This is by definition of just like a random like conditional expectation or conditional probability. Okay, we define the conditional expectation to be okay. If we have some random variable X and some condition, we just call that the sum of whatever value the X can take, given whatever the value that y was, okay? So this is all just like notation, notation sugar, notation syntax. It will be on the sides, right? And then, okay, if the random variable is continuous, you take an integral instead of a sum. Yeah? Okay? Like, yeah.
The notation, like that first equation, P subscript, like the uppercase X and Y, that's just implying the like uppercase X equals little x, right?
Oh yeah, so in this one, like we're conditioning on like, yeah, like we're conditioning on some Y and then say, okay, here's like, if I give you X and I give you Y, this is like this is how you can evaluate what the probability is.
Yeah, so it's like the notation, like the subscript notation is just like.
Oh, sorry, you mean this, you mean this part. Yeah, exactly. That's just like which distributions they're drawn from. Because it's kind of long to write this whole thing, like board space, right? Yes?
How do we get that second line? Is it just like long total probability? Is that what we're doing?
Oh, no. This is just a definition. We're just defining the conditional expectation as just this thing. So like the conditional expectation takes some value times the probability of that value happening, and in multiplying the probability of like that value happening, we need a condition on Y. That's it. Okay? All right. Here's some practice. So the practice is, okay, we got two six-sided die, D1, D2. Define random variable X to be the sum, and define the random variable Y to be the value of the second dice, okay? What is the expected value of X, given that we know what the value of the second dice is? Okay? Yeah, sure, maybe take a minute or two, think about this for a second. It should be pretty, you should just be able to just apply the definition, and it could be straightforward, but yeah. Chance to talk to your neighbor. I'll give out some more Kit Kats. Is it too easy? Huh? Okay, all right. Let's get some ideas coming out here. Okay, so what's one thing that we could do here? Yes.
To count it out. Okay.
Yeah. You could just count it out. Yeah.
Summary type.
Yep. Boom.
Right.
Count it out. Just take this giant, take all these numbers, right? And then okay, so you know that we're starting from 6. Just add 1, add 2 to all of them, right? And then just multiply the probability by 1/6, and you get 9.5. Intuitively, this is the same thing as just take the 6 that we already got, by linearity of expectation. Okay, it should be D2 here, but D1 and D2, same thing. That's equal to 6 plus 3.5, 9.5 both cases. Okay, make sense? Any questions? So yeah, I'm gonna call on people in the back more because this. Okay. Okay. So we're going to define g of y is equal to expectation of x given y, okay? So we want, in this segment, we're going to highlight that the expectation here is going to be a function of y. So y is some predetermined thing. We're going to try to take it as a function. So here's a black box of whatever y could be, okay? So the input is, okay, I guess we write that out explicitly. The input is, say, y is equal to 5. Okay, then what's the expectation over all the x's, given that y was something? I haven't told you anything about the probability, mass here, or the probability density here, or anything like that. So, but this function should just give us a number. It should give us an expectation over x if I tell you what y is. Okay? Likewise, if I say y is 3, okay, then this function might just tell me that it's 6. Okay, that's it. All we're trying to say here is this expectation of x given y equals little y is a function on y. Okay, it is not a number. Okay, so key point: e of x is a number, e of x given y is a function, and e of x equals say something like e of x equals 5 doesn't really make sense. Okay, so we can't this is a thing that we've seen in the past where students were oh yeah, we're running out of time on a piece of something, we'll write something like this, we'll be okay, we don't really know what to do with this. Okay, makes sense? Okay. So here's a few interesting stats that we collected. Like, okay, I'm pretty sure these stats are like from like 5 or 6 years ago, but it's still pretty relevant, at least according to trends. So here's like we have a joint distribution over favorite number and the year in school. Here's the marginal, meaning like, okay, if we just condition, if we just like say, okay, like ignore the year part and just take the probability over all the favorite numbers. These are people's favorite numbers. Everybody likes 7 because I guess like that's a jackpot in like a casino or something, right? Like 777 jackpot. I don't know. My personal favorite is 5. I'm very happy it's number 2. Good taste. So how do we actually calculate the expectation of this thing? You just sum each value and multiply by their PMF here. Okay. So okay, one tricky question is like, why do we know that all of these probabilities that is sum to 1? Like, what do we have to do to like make sure that all of these like sum to 1? Yeah, you marginalize. You normalize, marginalize, sum over to y's, divide. Okay. All right. So here's like a condition table. We're like, okay, so condition that you're a sophomore, your expected value, the expected number that you will like is like 5.5. Okay. Very tasteful. Number 5, great. If you're a junior, deviate a little bit. You're more likely to like a number around 5.8. Senior, 6.0. I think they meant 4.0 for GPA, but like 6 is also fine. And then if you're a 5th year, just go down to 4.7. Don't know. Maybe they also like number 5, but they just undershot it. Okay. Everyone see what we did there? So it's hard to like, we didn't want to write out the whole joint table on like a slide. It was kind of difficult. So like we took the expected value and used that as a representation. And that's exactly what the expected value should do. Okay. Okay. So yeah, this is another thing I like a graph. What the previous table looked like. And here is one about the expected number of units you're going to take, given which year you are at Stanford. Okay. Frosh? So, Frosh, oh my God, you guys are working hard. Like, the expected value of a number of units there is quite high. And then I think what happens is you realize you work too hard and try to take it a little bit slower in like sophomore year, but like kind of overshoot it a little bit. And you pick it back up in junior year, right? But in junior year, maybe you take a really, really hard winter. It's like, no, never again. And then senior spring, all of senior year. And then the 5th years that are left, like me, are probably just gunning for the units to actually graduate. So we have to step it up a little tiny bit. All right. The first time I saw this was pretty interesting because I think we took this particular value over over like CS109 in general. So like this particular group of like Frosh are like the Frosh in like CS109, and the sophomores in CS109. So it's like this is a distribution over like our class in the past. Yeah, it's quite biased. Yes.
Seen like a couple examples of things like this where like you've sampled like Stanford populations. Like, where is this data and can we use it?
This particular data probably somewhere on Chris's computer. I need to figure that out. But can you guys use it? Sure. I mean, like just like ask whoever has it. I think send Chris an email. We probably know where the data is. There's probably like some forms and documentation around it, but it should be okay. Yeah, great idea for an extra credit project. Yeah. Okay. All right, so I built in a little bit of a break. I don't know if it's halftime. I think I went over by 5 minutes, but yeah, let's give people like a 2-minute breather. Go use the restroom. Come up, ask some questions. I got some extra candy. Yeah. Have at it. Okay, all right. So it's been 2 minutes, I think, if the clock is right. All right, so let's come back a little bit and then start talking about the other parts that I have planned for the rest of the lecture. All right, so real question. What is this? What is this thing? So,
Expectation of a function, so it's a number.
huh?
Expectation squared.
Nah, it's like the expectation of an expectation. Okay. So what is the like let's consider expectation of x given y as a function on y, and then I take the expectation outside of it on y, right? Like what is the expected value of like the random? So this function right here, like expectation here, that's a random variable based on like whatever y is, and then we just like expectation over it. Yes.
Like on the previous example with the years versus the units, would that be like the expected value of like if we were to pick 1 year, like how many units would we expect?
Yeah, exactly. So the expected value of all the okay, so the expected value of x conditional y, trick shot, or it's just the expected value of x. That's it. That's it.
Total minus matter.
Uh-huh.
Minus matter.
It's because of this. It's because of a math trick. So we actually have a proof for it. Okay, so the proof here for why this tower property holds, like, okay, like in other math classes we call this like the tower property. It's pretty important, and actually like I think I used this one time on like a finance interview or something. It was interesting. But so here's a full math proof. Just spew. Don't worry about it for now. I will go over line by line with a cursor and some notes. So first line, we expand this using the law of unconscious statistician because expectation of x given y is a function of y. Okay, so click, great. Okay, law of unconscious statistician. Okay, so I get this big sum. Then by the definition of conditional expectation, I expand out the first term. Okay. Then I use a chain rule to smash back in the probability that y equals to y. Okay? And then I do this really like simple thing of, okay, switch the order of the sums here because like they're like the ordering doesn't matter on the sums. And it says x is not really like x doesn't depend on anything y here, right? Like every single one of these y terms is multiplied by like the same x. We can just pull it out. And then if we're going to sum over the joints of all the y, that's just going to give us the marginal on x. And if you just get the marginal on x, and then you sum over the x's here, that's just the expectation of x. Marginalized definition of expectation of x. Cool? Yeah, it's a tower. Yeah, this is tower property. I can go back and trace through this a little bit more carefully. Any questions? Yes.
Could you go over the first line again? How we apply the law of unconscious statistician?
Yes. That's because this thing right here, expectation of x given y equals little y, is a function on like we can view this as like a function on it's a function on little y. So whatever y value we can take here, we can just like say, okay, we're going to take the expectation of x over that because this will give us a value back. It's a function on y. Okay, makes sense? Almost. Yes.
Can I get intuition for this by thinking of e of x given y as a function over all possible y? It's the expectation of x over all y.
Yep.
And the expectation of that is just expectation of x. Is that why it's called law of total expectation?
Yeah, it's kind of like law of total expectation comes out of this, and it's actually a little bit simpler than this. But the idea is like, okay, we have the expectation of x given whatever we see on y, and then we take the expectation again over all the y's that we can possibly plug in.
Over all the y's.
Yeah, and then that comes out to just be the expectation of x. That's what this whole statement is trying to say. Yeah.
Generally, before we have an expectation of x, we do like 1 over n, right, times all those things. You know what I'm saying?
Yeah.
So why is there no term like that in this model equation?
Oh, it's because 1 over n if you have a finite sample. So like if you're like a sample mean, right? That's a slightly.
So just multiplying by x once I know this up. Is that the equivalent?
It's equivalent. It's
Okay.
equivalent. Yeah. Sorry.
Why is it called the tower rule?
Tower rule because I think the idea was like, actually, I'm not even sure why we call it a tower rule. I just saw it one time. We're like, oh yeah, this is a tower property. I think it's because if you keep chaining the expectations out, like you can we can make this longer, and it will still collapse down to a little y here, right? Like we can take an expectation of z and then pipe in another z into the conditional, and it will still give you back x. So it's like you can make the left side, like you can collapse the tower down to this little tiny thing. Although, like anytime. Oh, come on, cursor. There it is.
That makes sense.
Yeah, it's pretty cool. Here. Sorry. Okay. All right. So with that, here's the law of total expectation, and here's a little something I prepared. Oh yeah. This is key. Like this for the next problem. This will be the key. Just take the law of total expectation is you can condition on some y, and then multiply by the probability of y. Okay. This looks a lot like the law of total probability, except you put the expectation on the posterior. Okay? Posterior means the larger part. Cool. All right. So here's a little something from my past. So when I first came to Stanford, I wasn't sure if I wanted to be a CS major or a math major, and in fact, I actually wanted to do EE. But then I saw this one question that came up of like, okay, how fast does this line of code take to run? And I think I've been trying to figure this out for the past 3 years. And to be honest, I still don't know. So Netflix streams millions of hours of videos per day, so they really, really care about how long it takes to get a movie from their database. Okay? Here's a question. How long does this line of code take? Say you have a movie file that's 512 megabytes. That is not a movie. That's probably like a tiny episode of something, but 512 was the number that kind of worked here. And here's some options. Okay? Like, we live in big old land in all of introductory computer science, but for this particular segment and this particular problem, we're going to actually talk about like real values. All right, just real quick. Any takers here? Just choose one of these. One, right? Okay, 2. All right, any takers for 3? 3? All right, I think it's 4. The reason is because, okay, so it's very cheeky. They're all correct because it's a random variable. Let me explain why. So the reason is because I haven't exactly told you where this movie is. Like, is this movie stored on your computer? Is this movie stored elsewhere? Okay. So to see the first one, okay, your computer has the movie file. Okay, that's 0.3 seconds. You know, disk seek, read the throughput, load it into your OS, fire it off on your monitor. 0.3 seconds seems reasonable. Good computer, very good computer. If it's in SoCal, you got to go through some network hoops. The packet has to go to your router. The router has to go across some power lines and some telephone cables to actually get to your computer. That's going to take longer. That's going to be like 1.6 minutes. Okay? All right? So what if we go even more extreme and go to Japan for the file? All right, great. So now you go through cell towers and you have this giant under the ocean like pipe. There's actually like a whole pipe of just wires going under the ocean here that connect the internet from continent to continent. And you have to get the file that way. So that's going to take even a little tiny bit longer. It's going to take you 5 minutes to get the movie, right? Okay. We just want to cross the world in 5 minutes because of a giant internet line. So are we done? No. Right. Actually, though, somebody in space has a computer. Whenever someone has a computer, the first thing that they do is watch a movie. Okay? And when they watch a movie, somebody in space has a movie. Okay? Anyways, it probably takes them about 2 hours to get a movie. This is actually a made-up number. Like, I'm pretty sure, like, even if we like linked up all the satellites and do the little like optical thing, it's probably not even 2 hours. But like, tentative, like, depends on how things go the next 4 years. Maybe this site will live. Okay. All right. So what's the expected runtime? Our alien friend is back. So assume the file location is distributed with the following PMF. 10% chance is on your computer, because we're going to assume that you don't watch the same videos all the time. 50% of the time is going to be in SoCal, because people are going to be interested in the same movies across California. That's actually true. That's how they do some of the clustering for the databases. Probably that's in Japan. Okay, if it's not in Japan, it's going to be in space, my example. So I just put all the probabilities into Japan. Okay? Probably that it's in space. I hope it's not in space, because that will take you a long time to get the video, and I'm not sure which alien made it. So could you imagine coordinating a movie with aliens? Man, shooting that would be terrible. So what is the expected runtime of this following line of code, given that you have these particular expected values for your runtime? Okay? Yes?
Just give me do you want the answer?
Sure, yeah, yes, please.
The probability is multiplied by the runtime of each individual situation.
Exactly. So, sorry, what was your name?
Yes.
Okay, so suggestion was, let's just multiply each one of these values 0.3 by their probability, and then just sum them together, law of total probability. And that's exactly what we're going to do. So for home, we multiply, okay, get movie database time. I'm going to make a very long name for it because good style. Multiplied by the probability that it's at home, and the expectation is going to be conditioned on that it's in your house. Okay? That's the first term. Do that for all the other terms, and you just plug and chug all the values, and you get the raw numbers. Okay? Multiply them together, you get 6.25 minutes. Just some value out there. On average, it's going to take someone 6.25 minutes. Okay? All right. Now, another interesting thing we can do is, okay, let's take this single line of code and actually wrap it in an if statement. It's let's pretend that your computer actually has a cache that can take more, take in more movies. Okay? There's an 80% probability that the movie is in your local cache, in your computer cache. And getting a movie from the cache takes the same amount of time as getting a movie from your local computer, because they're both on your computer. What's the expected runtime of this? So here's a trick that I kind of want people to see is, if you have an if-else statement here and you want to take expectation, do the law of total expectation based on the branches. So if-else here, law of total expectation, first term will come from the if, second term will come from the else. Okay? It's exactly this. Just, okay, get the values. Here's your first term. This is from the else. Okay, I put the else first and then the if second. Okay? We already know this value up here if the movie is not in the cache. That's just a database read, right? So that's just the expectation of whatever we had from the previous slide. Multiply that by 6.5, add them together, 1.2. Okay? The important thing is, we didn't have to redo the work to get this 6.25 minutes. Okay? Following? All right. Let's do one more thing. What if you have many files? So I just wrap that if-else statement inside of a for loop. Okay? Assume we are interested in n movies. Assume the retrieval time of a movie from the old cache takes 0.3 time. What is the expected runtime? And what is the approximate distribution of the runtime? Okay, approximate distribution here, we have sum. Assume all of the movies come in IID. Yeah, normal, central limit theorem. It's exactly normal here. And then in the normal, the mean is n times the expected value for each one of the movies, so n times 1.2 minutes. Okay? All right, great. So with these three pieces combined, we've actually implemented one of these little dots. So here's a giant map of Netflix's cache location maps that's stale by 2 or 3 years. So they probably have less now because I think they migrated over to AWS. In each one of these dots is a building called the Internet Exchange Point. So it's just this giant building that houses, well, servers. Probably has some really good air conditioning. Good place to work. Okay? Within each one of these servers, running a big chunk of code that we just basically implemented. So especially maybe it's too small to see. Batch load was the last example we saw. This if-else statement is the example that we saw 2 examples ago. Okay? That's it. This is how Netflix does cache locality for all of the databases. Well, okay, very simplified, very simplified. There's a lot more underpinnings in it, but this is kind of the general idea of how you would do caching. Okay? Oh, by the way, here's the full code. And why would they care about the expected value? The initial functions can distribute a copy per geolocation. The getting the movie, you can say something about like, okay, the average customer could get a clip in 1.2 minutes. While the user is either watching other videos or asleep, you can do a batch load and load all n of the files or all n of the movies. Okay, so this is just a concatenation of like we did this on the third example. This is the second example. This single line is like the first example, or this single line is like the first example. That's it. And we're calculating the expected value over all these, and they can use these metrics for the like video quality team or for like other people trying to stream services over Netflix and sell them like, hey, here's some streaming capacity for your video. Like we'll charge you X amount for it, and here are the guarantees that we're going to put for that like particular stream. Okay, those are called SLOs, service level objectives. Not that important. This is just like an example to get people warmed up for like expected values in algorithms. Okay. All right. So that's it for Netflix. That's it for our little friend, the alien. We have a little bit more of a dry problem afterwards because it's grounded in theory land. I shouldn't say dry, actually. It's a pretty interesting problem too, but it's I couldn't find a very good story for it other than, hey, this probably helps in 161. Okay? You have recursive code. You take each time you hit the recursion, you take a random value between 1 and 3. If the value is 1, you return 3. Okay, that's it. If the value is not 1, if it's 2, you return 5 plus another iteration of your recursive code. And if it's not 1 or 2, which means it's 3, then you return 7 plus whatever your recursive code returns. Okay? And then the question is, let y be the value returned by one iteration of recurse. What is the expectation of y? Okay? So the thing to note here, what do we have? We have an if-else. When you see an if-else, the first thing that you do is the law of total expectation. Okay?
Why does that make sense?
Huh?
Why does that make sense?
Oh, because every single time you go down an if branch, you're conditioning on entering that if branch. And the condition and conditioning on like the if statement right here, right? These if conditions are all like random variables. They're all like conditioned on like whatever x takes. So every single branch of these can be thought of as like a posterior distribution across like the x. Okay. Okay. So just fire off the law of total probability. You have the expected value of like, okay, like y, which is this value here. So y is like recurse, given that you've seen x equals 1 times the probability that you went down this branch, and then given that x equals 2, given that x equals 3, et cetera, you just expand out using the law of total expectation because you have an if statement. Okay? So we take each term and we can unpack them. The expected value of y, given that x is 2, right? That's the second if statement. And it actually ends up just being like 5 plus whatever you recurse on. So by linearity of expectation, you can just say, okay, expected value of 5 is 5. Expected value of a constant is a constant. Plus the expected value of recurse, which is exactly what we have right now. So expand all of these, and then we can plug them back in. By the way, any questions here? People following? All right, cool. So we have so we know what the probabilities are because it's a random integer uniformly, and we now know what the expected values are. We can just plug them in, and now notice you have expectation of y on the left-hand side of the equation, and you have expectation of y on the right-hand side of the equation. But importantly, you also have a standalone. You have a standalone constant, which means that you can subtract over all of your terms of e of y, and then solve for e of y. Okay. So you can just subtract like, okay, like there is some math unpack here, but it's mostly just algebra. You like subtract, okay, like a third of a y over here. You subtract like another like third of a y over here, and then you subtract like 2/3 of a y expectation of y over here, and then you can just see that that's going to be equal some constant. Yes.
If we didn't have that standalone constant, then wouldn't this imply e of y equals can be anything?
It can be, yeah.
So like what if like we had if we just had like instead of like 3, 5 plus recurse plus this, but like if recurse, if this thing then recurs, if this thing then recurs.
Yeah.
Like would like we resolve the paradox by saying the algorithm doesn't terminate then, or like?
So your expected value of y would actually be infinite. It would diverge because you would just keep summing. Yeah. Okay. Any other questions about this? Did I go too fast? I could go back a little bit and like see if there's something. Yes, in the back.
Yeah, I think just that last step of going from
Okay. So this last step, we substitute in e of yx, right, into all of these terms, okay? So we see here that there is like a standalone like 1, like 3 times 1/3 is 1, right? And then there's like a term for e of y here. There's so 1/3 term for that, another third term for over here, so that makes 2/3 of a term. And then here we have another 2/3 of a term of ey, okay? So 2/3 of ey here, 2/3 of ey here gives us 4/3. So we can just subtract 4/3 from both sides and get negative 1/3 of y is equal to whatever is equal to like the remaining constants on the right. Then you divide both sides and you should get a value for expectation y. Does that make sense? Very hand wavy. Sort of. Yeah, like what I recommend is maybe like in your own time, like take a look at this side and actually just make sure that like you can solve for e of y here. It's a very like algebraic computation. Okay. Yes, you have a question?
If we modify this algorithm to say x equals random int 1, 2, and then we also say x, like if x equals 1, then return recurse minus 1. If x equals 2, return recurse plus 1, so that it's perfectly balanced, that constant term cancels out, but it's still the algorithm might or might not terminate there.
Oh, but your expectation is going to be fine though, because it will terminate in expectation.
It will terminate in expectation.
Yeah, it will terminate in expectation. If you don't return ever, you will not terminate on expectation because there's not a single case where you would terminate. But if there is a case where you could terminate, then there might be a chance that in the expectation you will terminate.
I see.
Yeah. Okay. All right. So let's move on. Pro tip: use this in 161. This will be very useful in that class. Also, like on a finance interview about like coin flipping, but that's a tangent. Here's a few things about differential privacy, and maybe like the last 3 minutes, I can just go over this like quite quickly. It will not do it justice, though. Like, please look at these slides on your own. But like, so here's Cynthia's work, and she aims to like provide means to like maximize the accuracy of like machine learning models, with a low probability of them actually identifying the data set you trained on. This is particularly helpful in medical AI, where like a lot of your data is IRB like shielded, meaning like people can't or should not be able to look at your training set. And if you publish a model trained on like health sensitive data, that's a big issue if people can reverse engineer a model to get your data set. Okay? So to account for that, we do a thing called obfuscating, which just means, hey, for everything, we're just gonna inject a random noise into the labels, and with some random probability, some training set will just get injected with some noise. Okay, and then we train a model on it. So someone might actually ask us, okay, what's the expectation that someone could actually extract the xi here, like in an equation like this, right? And what we see is that like, okay, this random over here is like a Boolean between true and false. What's the expected value of whatever the output is we get here? That's just equal to the probability that like, okay, so e of xi equals like probably that y equals 1, which because they're both of these are Bernoulli. Probability is like, okay, law of total probability, if else branch. If branch, you get the 1/4. Else branch, you get whatever the original p was. Okay? Sorry, okay. Okay. So say someone went in here, took a sum over all the values, like they ran your model many, many, many times, and then they took like some sample average. Would they be able to extract out whatever this p-value is? Turns out they could get some estimate. They could say that the expected value of like whatever the z is equal to like 50 times p plus 25. How good is this estimate? That's an open research problem, and it's being explored by Omar. Omar Ringgold, yeah, the guy that used 154. Okay, so that could be a challenge. You could use this as like a extra credit project or so, but it's something that exists. And then here's the paper that was written about this. And it's still like, yeah, it's an active area of research. Differential privacy is a big thing. I did a project about differential privacy back in 229. It was really fun. It's a good area. This is just like another way to like use expectation in like algorithmic analysis. Okay, so that's it. Today we ended the algorithmic analysis part of CS109. Next Monday we will start doing machine learning. So MLEs, MAPs, all the big names. They're really cool. It's a very fun section. Thank you guys for coming. Have a good weekend. Yeah.